today's topic is about the motion of the planets. I don't usually do this, but I think it's somewhat interesting. I'm going to start with a teeny bit of history. I don't know a lot of history, but I know a little bit. So as you probably know, sometime around the 2nd century, so that's like 2,000 years ago, there was a Greek philosopher, astronomer, Ptolemy. And he worked out the motion of the planets. Now, how did they even know there were planets? Well, people look at the sky a lot, okay? When you have nothing else to do, you look up, right? And they noticed that at a particular time of year, let's say when some crops come up or something like that, that every time during that year, every year, the objects in the sky, the points of light, were always at the same spot. They were always the same place at the same time of year, except for a few. They noticed a few, like 5 or 6. And these were the planets. All right? And they figured out that these were moving a lot more than those other guys were. So they didn't know what they were, but Ptolemy decided to work out what their path was from his point of view. So what he did was he decided to set his origin for his coordinate system right here on Earth, probably someplace in Greece. Okay? So that's what he did. There's nothing wrong with that. Nothing. We could put our coordinate system anywhere we want. And then after him, people elaborated on his description to get better and better calculations and predictions of where the planets would be at any time during the year. And these predictions were very accurate, extremely accurate. It's amazing how much they could do knowing nothing about physics, really. It's just purely looking at the sky, observations, and making predictions. Now, a lot of people say Ptolemy was wrong. The planets don't go around the Earth. They go around the sun. And the Earth goes around the sun as well. Well, I think that point of view is somewhat wrong itself, because you can choose any reference frame you want. Along comes Copernicus in about the 1500s, I think, late in the 1500s sometime. And he decides the planets go around the sun. The only reason why that's better is that it's simpler. It's so much simpler. Because what happened with the Ptolemaic system is it get more and more and more complicated. You had to keep adding extra effects, so-called epicycles, to get more and more accurate. But Copernicus was able to provide a very simple description of what was going on. He still had no idea why the planets went around the way they did, but his description was simpler. And using what's called Occam's razor, that we like to use in physics, namely the simpler is somehow more accurate, truthful, something like that, is better. The reason why the Copernican idea is so important is not just because it's simpler, but because it allowed for more advances later on. Okay? So scientific theories are not just evaluated on how accurate they are in prediction, also evaluated how well they lead to further developments and more understanding. And they did. Next came Kepler in the early 1600s, I believe. He was able to take those observations and provide what are called Kepler's laws that describe in very simple ways the motion of the planets, what they look like. And he was able to find some regularities in those descriptions that we will derive today. So that was a great advance. But still, no physics, really. All it is sort of like math, describing the orbits of the planets. That's all it is. There's no model for why it's occurring. And then along comes Newton in the late 1600s, and he provides a reason for why the planets are moving the way they do. All right? And he provides a law for gravitation that we'll put up in the blackboard in a minute. And the importance of this, the great advance, unbelievable advance, is he not just was able to describe the planets with his model, but the same model also described motion on the surface of the Earth. So that is the key advance. The idea that the planets are not some supernatural thing, some extra thing in the universe, different than what's going on Earth, but it's all part of the same thing. They all follow the same laws. And this movement in physics towards more and more universality, encompassing more and more effects and more phenomena, is what has made physics so powerful as a science. So it not only has this power of providing all this universality, but it, in addition, is very useful in all kinds of applications, right? All your cell phones, everything, this speaker, everything we've developed technology ultimately derives from some physical principles. So I'm going to start by showing you some orbits of planets, right? I'm not going to tell you where these come from, at least not yet, but just to provide a sense of what they look like, all right? So I have this simulation that I've done. At some point, I might tell you how it's done, but it's mostly just to give you an idea. The red guy is the planet. The black guy is the sun. All right, so it goes around in a circle. Isn't that exciting? Okay. Actually, when I first started doing simulations and writing these programs, I went to a conference 30 years ago to show how you can use the computer to illustrate ideas in physics. And we had two computers set up. One computer was showing something like this, and another computer off to the side was showing some really interesting chaotic phenomena, all right, like a double pendulum, and the pendulum was going in all kinds of crazy ways. Everybody was looking at this, not at the other thing. Right? They found this fascinating. Now, of course, it's not so exciting that it's going around in a circle. It can do many other things. All I got to do is change the initial conditions. All right, so the initial conditions are given over here. There's an x coordinate, which I give 1. Vx is 0. Y is 0. Vy is 6.28. So that means it starts here, and it's going up. Well, I can change one of those coordinates. For instance, I can make the velocity bigger. So I could do that. Make it 8 instead. I initialize it. It starts at the same place. I still don't need this. And then I start it. And you get an elliptical orbit. Okay? Notice one important result here is the sun is not at the center of the ellipse. It's over here. It turns out that this is the location of one of the, what do they call it, the foci of the ellipse. The sun is over there. The sun is also fixed in space, We assume it's extremely massive, and we don't have to worry about its movement. All right, I could change this in many different ways. And as I'm going to make this initial velocity a little bigger, I think around 10. Initialize it. We don't need this again. And then start it up. All right? All right, now we can wait a while to see if it ever comes back. I can't remember. I don't think it does, or I don't have time to wait. All right? So for certain initial conditions, this planet goes off to infinity, and we will learn how to figure that out. And for other initial conditions, it goes in an orbit. Those orbits can be circular. They can be elliptical. Okay? And it turns out that this orbit is basically hyperbolic. It follows a hyperbolic curve. That's what we know. Now, how do we explain this? All right, that's what we're going to do now. All right, so what was Newton's great achievement? His great achievement was the following. We're going to remember, on the surface of the Earth, we have a gravitational field, which I call G, and it's just equal to 9.8 newtons per kilogram and down. So this G that you're all familiar with is the gravitational field. And why that's important is that the force on an object is just the gravitational force. It's just the mass of the object times G. So this is the mass of object. Okay, so the force on an object is the mass times the gravity. This field concept is very important. We won't use it a lot this semester, but next semester it's all about fields. Even though I'm not going to be teaching it, it's all going to be about fields. Isn't that correct? Yeah, a lot of fields next semester. So you might as well get to know what it is now. What is a field? A field is the following. Every point in space has a value. Not only does it have a value, it has a little vector value at every point in space, and that is the gravitational field. Whether there's an object there or not, doesn't matter. There is a gravitational field. What is that field due to? It's due to the Earth. It could be due to the moon. It has a very small effect. It could be due to the sun. It has another small effect. It could be due to you, even smaller effect. Okay? These, all the objects in the universe provide fields at every point in space. All right? And then the net field at that point, how do you get that? You just add up all the gravitational fields due to all the objects in the universe, but you have to add them factorially. So what does that mean? That means if I have an object over here, so that's going to provide a gravitational field maybe like that, and maybe another object over here. And at this point, it'll provide a gravitational field, let's say like that. Maybe it's a little bigger because it's closer. Then the net field due to these two, you know, I just have to add these two up, might be something like that. So this is G. All right? So for this lecture, G is not necessarily 9.8. G is the gravitational. So far, I haven't gotten to what Newton did. What did he do? All right, let's see what he did. So Newton's advance was to figure out what the force law, or the value of the field is at different places in space. So Newton's idea is the following. So this is the universal law. Now, I don't know if universal law of gravitation. Now, I don't know if Newton actually spoke in terms of fields, but I will. So it's kind of a modern version of what he did. So the basic idea is that the field is given by minus gm over r squared r hat. So what does that mean? Here's the object of mass m. Here's a vector going outwards. And my little r vector, r hat, is like that. And we're calculating the field right there. So we want G right there. All right? The minus sign means that the gravitational field is towards the object. All right? And it's in the direction of this unit vector, r hat, in that direction. And its value is gm over r squared. Okay? So that's the universal law. You can look up what g is. It's a pretty small number, which is why gravity between you and I is very tiny. All right? Let's see if it's something like 6 times 10 to the minus something. G is 6 times 10 to the minus 11 in MKS units. So you need a lot of mass to generate a reasonable gravitational field. Okay, so here's the value of G right here. And of course, that ultimately leads to a force by this result, Fg equals mg, and that equals gmm over r squared. Okay, so this is the magnitude of the force on a particle of mass little m due to an object with mass capital M. Okay, any questions? All right, so this result, you can use this for any situation where you have spherically symmetric mass distributions. So in other words, if I have a ball like the Earth or the Sun, it's pretty close to being spherically symmetric. Outside of that ball, that'll be the force. If it's not spherically symmetric, then you have to deal with every little piece of mass inside the object and add it up, the gravitational field to each part. We won't be doing that. Okay? All right? I might mention what some of the effects of that are a little later. So now I have a question for you. All right? So my question is over here. The radius of the Earth is about 6,400 kilometers. You know, there's a shuttle. I think it's still up there. It's still up there, right? There's some kind of base up there where I think there are astronauts up there. I think they're mostly Russians right now. That orbits the Earth around 320 kilometers above the surface of the Earth. I want you to find the gravitational field at this height, 320 kilometers above the surface, and express your answer as a multiple of G at the surface. And that G is 9.8. So how do you get G at the surface? You just put in the radius of the Earth right here. Okay? So everybody do that. I want you to find out what the gravitational field on the surface at 320 kilometers is compared to what it is right here. All right? And all you got to do is see what effect this has. All right? Figure it out. What must it be? You don't have to know the mass of the sun or anything. You don't even have to know G. All you need to know is what R is, because I'm interested in a ratio. I want the gravitational field at 320 kilometers above the Earth compared to the gravitational field at the surface. That's what I want. Okay. So the answer is, so G for the shuttle, the field at the shuttle. So this is the field at the shuttle divided by the field on the surface of the Earth is roughly about 0.91 maybe, something like that. It's not that much different. The field does not go down that much because 6,400 is so much bigger than 320. All right? So if the field is not that big a difference, why do astronauts and cosmonauts, why do we say they are weightless? Are they really weightless? Right? The word weightless in English means no weight. Right? They're just floating around in their little shuttle there. Why is that? Any ideas? This is something they probably talked about in high school, right? Don't they? Probably. Right? So why would this be? Did the astronauts all of a sudden lose lots of mass out there? Maybe because they don't feed them very well? Is that why? What's going on? Has any of you ever been in a weightless situation? Okay. Here's the answer. If your acceleration equals g, you are weightless. Why do you think that is? Why are you weightless if your actual acceleration equals the acceleration? Can you give me an example where that might occur? What was that? I can't hear you. All right, you jump. If you jump off the roof of this building, for those few seconds when you're still alive, you are weightless. So those of you who are overweight, here's a way of reducing your weight. All right? Because your acceleration is exactly equal to g. Weight that you feel is nothing to do with gravity. What force do you feel? You're sitting on your butt. What force do you feel? A normal force. That's what you feel. So when we measure weight, like any way we measure it, we're almost always measuring normal forces. We're not measuring the gravitational pull of the Earth, even though we call that the weight. Okay? So up in the shuttle, this shuttle is going around in a circle, right, around the Earth. Its acceleration is identical to g. All right? Otherwise, it wouldn't go around in a circle. Right? There's only one force on the shuttle. And the same force is on every object in the shuttle. And what force is that? What force is that due to? What force is that? Is gravity, the gravity of the Earth. That's the only force there. That causes it to go around in a circle. Okay? And therefore, the acceleration is equal to g. Okay? So that's how it works. Remember this movie, 2001: A Space Odyssey? Anyone ever heard of that? Stanley Kubrick was the director. There was no famous actors in it. but it's probably one of the best films ever made. I think it is one of the best films. Right? And it's one of the few that has the physics reasonably well done. Okay? And in that movie, they have a satellite or a space station. That's right. Space station out in space. And the neat thing that Kubrick put in was that the space station was rotating on its axis. By doing that, it was able to simulate gravity on the Earth. Right? And so the astronauts could walk around as if they were on Earth. And nowadays, in a lot of good sci-fi movies, you'll see that. The bad sci-fi movies like Star Trek, you don't see that. All right? Star Trek's ridiculous. All right? There's hardly any correct physics in there at all. All right. Okay, so that's why you're weightless. Weightless means your acceleration is the same as the gravitational field, same value. Under those circumstances, you will be weightless. All right. Now, I want to introduce a key idea here. Notice the gravitational field has a value at every point in space, and therefore the force on an object just depends on where that object is. So that means gravity, just like it is on the surface of the Earth, is what we call a conservative force, and there's a potential energy associated with that force. All right, so let's calculate what the potential energy is. So the gravitational potential energy. All right, so if you remember, this is given by u at some position r minus u at some reference position. And I'm going to call that position r equals infinity. All right, so this is the position relative to the object that's producing the force. Okay? So here's my object, mass m, and here's r. And I want to know what the field is right there. Okay? And I know what the field is, I can compute the potential energy. Remember, it's minus the integral, and you go from infinity up to r, and then we have f dot dr. All right? And what we're going to be doing is we're going to go along this radial thing. We're going to go from here all the way to infinity, but we're going to do it radially. We're going to take the path radially. We could do any path, but the radial path is the easiest one to do. It'll be the same independent of path. Remember, we worked that out for conservative forces. The potential energy at this point compared to this point is the same independent of how we got there. All right, so the easiest thing is the radial path. So we write this, f dot dr. So f is this way, r is that way. So that means we have another minus sign, gm m over r squared dr. So here's the force on an object right here. And we imagine taking this object from here out to infinity. All right? So the two minus signs cancel. And then we get the integral of this. Anyone know what the integral of that is? These are just constants. what's the integral of 1 over r squared? What function, when you take a derivative, will give you this? So the integral is just an antiderivative. What function, when I take the derivative of this, what function, when I take a derivative, gives you this? Everybody should know this. dx to the n equals what? What does that equal? It's n minus 1 times n, right? N times x to the n minus 1. Everybody know that? Yeah? All right, so now we're going backwards. We're looking for this function here that gives us this. All right, so my n minus 1 is n minus 1 is minus 2, right? Is that right? Yeah. So that means n is equal to minus 1. And so what I get is over r, and I get a minus sign. Right? So if you do this integral, you do this. All right? And then you're supposed to evaluate it at the limits from infinity to r. And so you get gmm over r. Because 1 over infinity is 0. And it's a minus sign. Okay? So this is the answer. We're going to assume this equals 0. We're going to set infinity equal to our origin, our reference point. So at infinity, the potential energy is defined to be 0. We could define it anywhere we want. I could define the floor to be 0. I can define the center of the earth to be 0. I can define the center of the sun to be 0. Those definitions turn out to be not too useful. It's much better to define infinity to be 0. And you'll see why in just a second or a minute. Second's too short. All right. Okay. So now we have this result. This is the result. And you want to have this. This is one you want to have memorized. U gravity at r is minus gmm over r. All right, so that's what's called the gravitational potential energy. Now, let's imagine we have a particle over here. All right, and I asked the question, what is its total energy? Now remember, you saw those those orbits of the planet. In two of the orbits, the circular and the elliptical orbit, the planet stayed in its orbit. And in the third one, the planet went off to infinity. So my question is, what's the key quantity that differentiates the bound orbits from the unbound? Bound orbits, that was circular, elliptical, and what it means is r is always finite. And unbound means r goes to infinity. So let's see if we can figure out what distinguishes bound orbits from unbound. Okay. Let's say you're a particle. Now remember, this is a conservative force. What does that tell you about energy? What does that tell you about the total energy of the system? This particle is moving around. What is that? Well, there's kinetic energy, right? And what can we say about the total energy? Kinetic plus potential. What can we say about that? So when the planet's over here, it has a certain energy. Then when it's over here, it has an energy. When it's over here, it has an energy. Over there. That energy is its kinetic energy plus potential energy. What can you say about that energy at different points in the orbit? What? It's the same. Probably nobody heard her say that, but that's what she said. She whispered to me, it's the same. Okay? It's the same. Energy is conserved. Now, let's imagine that this particle goes off to infinity. All right, so I'm going to have it go off to infinity. Remember, we put in 10 there, initials. All right, so this guy, keep forgetting to get rid of this, is going off to infinity. What's its potential energy at infinity? Zero. What's its kinetic energy at infinity? It could be anything. Can it be negative? No. Kinetic energy is always positive. So if a particle goes off to infinity, that means the total energy is greater than or equal to 0. All right? Total. All right? And E total equals the gravitational plus the kinetic energy. Okay? This is true even if you have more than one object, like the Sun plus Jupiter plus Saturn. All right? You still will have the situation that if the total energy is greater than 0, the particle will eventually go off to infinity. The only thing that will prevent that is if it collides with something. So that's an unbound orbit. So that means for a bound orbit, E total less than 0. All right? So the total energy for a bound orbit is negative. All right? So this result is true for any potential energy, any kind of force, as long as the potential energy is defined to be 0 at infinity. Can you think of an example of a potential energy that you know about where that is not the case? Where the potential energy is not defined to be 0 at infinity. It's defined to be 0 somewhere else. You only have two choices because we've only talked about two potential energies in this course. Can anyone think of one? What? The spring. Right? The spring potential energy is definitely not 0 at infinity. It's infinite at infinity. The spring potential energy is always said to be 0 at its equilibrium position. So some people forget about that and always use this, but this is only true if the potential energy is 0 at infinity. All right, now I want you to use this fact. I want you to find the escape velocity from the surface of the Earth. What speed do you need to go at if you're at the surface of the Earth? You don't have to put numbers in. Just represent R by RE. That's the radius of the Earth. And just leave G and M. M is the mass of the Earth. All right, so figure out what is the escape velocity. That means the minimum speed such that the total energy is equal to 0. All right, so figure out what that is. Shouldn't take you long. Hopefully you found it. All you got to do is take this formula here. You have GMM over RE minus plus 1/2 mv squared is equal to 0. Right? That's all you got to do. All right, so that's the escape velocity. So V escape is equal to what? 2gm over RE square root. All right, so that's the escape velocity. All right. So in getting rockets to escape from the Earth, we need to do that. One very important result of this is the fact that there is no hydrogen or helium in the atmosphere, even though most of the universe is made up of hydrogen and helium. And probably in the beginning, the Earth was made up of that. Why? Well, one of the things we'll learn later in the course, is that all the particles in the atmosphere have roughly a similar average kinetic energy, which is determined by the temperature of the atmosphere. So the temperature and the average kinetic energy is roughly, they're proportional to each other. So all the particles have the same kinetic energy. And so if they have the same kinetic energy, that means that if m is small, the escape velocity, the velocity is large, and it's large enough to escape. So the gases with small masses, they have the same kinetic energy as gases with large masses, but they have larger speeds. And that speed allows them to escape. So there's essentially no hydrogen in the atmosphere. There's essentially no helium in the atmosphere. There's hydrogen in your body and in lots of things like fossil fuels. It's all over the place. But that's because hydrogen bonds with other things. But helium does not. Helium doesn't interact with anything. There's no compound that I know of with helium in it. Right? So that's a little bit of chemistry. So helium, even though it's one of the lightest elements, was one of the latest to be discovered. In fact, you know where it was discovered? It was discovered on the sun. They discovered helium on the sun. They never discovered helium on Earth. And the way they did that was they learned about spectroscopy, and they learned that the spectroscopy was a signature of different elements. And they were able to discover that helium was on the sun. In fact, the sun is made up of a huge amount of helium and hydrogen. All right, so helium comes from that. Right now on the Earth, there's a little bit of helium trapped from fossil fuels from God knows when. And then there's some helium produced in radioactive decay. So alpha particles, for instance, are helium nuclei. And nuclear reactors produce helium. So that's where we get our helium, which we use in physics. We use it as in cooling, coolants, refrigerators, to get things down to very low temperatures. All right. So Copernicus determined or modeled the orbits of the planets, that the planets went around the Earth. Okay? And he didn't really know what kind of orbits they went around. He probably thought they were circular. And in fact, they are pretty close to being circular. But Kepler, he had more advanced, careful observations. I think he also, his mentor, Tycho Brahe, did very careful astronomical observations. And so they knew the orbits very well. And so Kepler was able to take that data and determine the properties of the orbits. And the first thing he realized was that the orbits were elliptical. They were pretty close to being circles, but they were a little bit off from circles. They were ellipses. All right, so that's what's called Kepler's first law, that the orbits are elliptical. Now, that may not seem such a big advance, but it's an incredibly important one, because people noticed, astronomers noticed, that some of the planets had orbits that were not quite elliptical. In other words, they kind of deviated a little bit, and in fact, they didn't even come back to themselves. Remember how those orbits came back to themselves? They just retraced their orbit. So in the late 1800s, middle 1800s actually, they were so good at this, I can't imagine how they did the calculations, all right? Because it's pretty hard to do. They realized that one of the planets, namely Uranus, its orbit wasn't quite what they expected. It would not come back to where it was. It would, they call it precession, another word, use of the word. Let me show you what that means. So here's two planets. The sun is over here somewhere. Okay, I forgot to put it in, but it's there. Okay, so here's what happens. All right, so you have two planets. All right, so notice that the inside planet does not quite follow the right orbit. It doesn't retrace its orbit. The reason for that is that this mass interacts with that guy. Right, so there's a gravitational pull of one planet on the other. Okay? The outer planet doesn't do much. It seems all right, partly because it's further away, and partly because it probably has a smaller mass. Okay, so they saw this. So when they saw this kind of orbit, they said, aha, there must be another planet somewhere that we haven't discovered yet. And they could figure out from this orbit roughly where the other planet was. And then they started looking for it, and they found it. So just think about this. In the 1800s, you're looking up at the sky. You look carefully at the orbit of one planet. It's not what you expect. Tiny little deviation. This deviation that you see here is much, much larger than what they showed you. All right? I make it bigger so you can see something. But they could barely see anything. But they could see that it was not quite right. And then they figured out where Neptune would be. And sure enough, it was there. They found it. Actually, there was a little bit of serendipity. They really looked at the wrong place because their calculations were slightly off. But anyway, they found it. Right? And Neptune was found. Okay? So the astronomer who did this got very famous. I forget his name. I think it was some French guy. And they started looking at Mercury, the planet closest to the sun, And they noticed that that planet also did not quite do what it was supposed to do. In fact, what they did was they even put in the effects due to the other planets, like the Earth, Venus, Mars. But those planets were so small, they didn't have much of an effect. They could figure out what it was, but it was not enough. And the amount of precession we're talking about, the deviation, like when it goes around and then it just barely misses and then eventually it comes back, was like a huge, tiny, tiny thing. It's like a few arc seconds per century. What is an arc second? Well, a degree is 1 degree, a minute is 1/60th of a degree, and a second, arc second, is 1/60th of that. It's a tiny, tiny change. But these astronomers were so sure of themselves, they knew there was something wrong with the orbit of Mercury. And because of their success in finding Neptune, they thought there was another planet inside the orbit between Mercury and the sun. And they started looking at it. They started looking for it. And some people said they saw it, but they couldn't reproduce the result. There was a famous solar eclipse in the late 1800s. That the best way to see this solar eclipse was in the western part of the United States. And all kinds of people, astronomers, famous industrialists, went out there because they thought they would be able to see it. And again, they kind of thought they saw it, but it was not quite there. So this went on for about 20 years. They even gave it a name. They called the planet Vulcan. Vulcan is like the god of fire or something like that. Okay? They never found it. By the end of the 19th century, the late 1800s, they pretty much gave up. All right? So this happens in physics. You have this really difficult problem. You work on it harder and harder and harder. You can't find the answer. Nobody knows what to do, so you move on to some other problem. All right? Because what are you going to do? Well, the answer came in 1915. All right? It turned out that this was not right. That Newton's theory of gravity was not quite right. Albert Einstein, he took his ideas about special relativity and he applied them to accelerated reference frames and to gravity, and he developed a new theory of gravity that gave results that are only slightly different than Newton's theory. But they had some other nice features, some of which we've just discovered in the last 5 years. Okay, so one thing that Einstein was able to do was to apply his theory to the orbit of Mercury, and he was able to predict the precession precisely. Also prove that light would be bent in a gravitational field. And the only way of testing that was during a solar eclipse, which I think they did in around 1916 or 1917. All right? They went, a whole bunch of people went to, I think, I don't remember where they went, someplace in the southern hemisphere, right? And they looked at it, and sure enough, Eddington was the leader of the group. They found that the light went. And the reason why they needed a solar eclipse is because what they did is the solar eclipse blocks the light from the sun so that starlight going near the sun's surface could be still seen. So you needed to look at stars that were, shining light very close to the surface of the sun, because that's where the effect would be biggest, and then they could measure that, how much it's bent. And it was bent by the right amount. The first story was that they couldn't see it, all right? And Einstein said, well, they didn't do it right. Right? He was so sure of himself that it was right, and eventually they tested it as right. Okay? So the general theory of relativity has stood up. Another prediction that Einstein made was that there would be gravitational waves coming from huge objects that could come from huge masses. All right? And he predicted how you would figure them out. But they were so tiny that it's taken almost 100 years to actually discover, measure an actual gravitational wave. And it was done about 5 years ago, I think, something like that. All right? They have these huge arrays where they shine laser lights back and forth. And the distance between, they're like a few kilometers long, the distance between the ends where there are two mirrors, that distance will deviate by some tiny fraction of a nanometer, I think, due to a gravitational wave, and they could detect it. How do they know they detected it? Because they have another one just like it somewhere else. So they have two of these, one in Washington State and one in Louisiana. And they watch the signals, and if the two signals match up at the same time, they got it. Then they know the signal's not due to, like a truck passing by on the road. All right? So that was discovered about 5 years ago. And have they already won the Nobel Prize for that? Yeah, I think so, right? So that was a big discovery. It's going to open up astronomy. Because astronomy now, not only started with looking at visible light, then we had satellites so we can go up and look at X-rays and ultraviolet light and infrared light. So we can do that. We can use radio telescopes to look at radio waves. Now we can look at gravity waves. And just a couple years ago, they actually had a gravitational wave signal from a position in the universe. And simultaneously, they had a visible signal matching the event. All right? I think all those events were basically, the first one was two black holes merging. The second one, I think, might have been a huge black hole and a neutron star or something like that. All right. So anyway, this is an interesting result. What about Kepler's second law? All right, so Kepler's second law says the following. One of the things you probably noticed in the simulation, so it goes in here's the star, and the planet's going around like that. When it's over here, it's moving faster than when it's over here. So if we take a fixed time and we ask how it moves, so like in a fixed time, maybe it moved that amount, and we take the same time over here, this area and this area are the same. So that's Kepler's second law, that the area swept out by the orbit is constant throughout the orbit. And that's just the consequence of conservation of, what do you think? Is that what do we know? Conservation of energy, conservation of momentum, conservation of angular momentum. Which one do you think it is? Angular momentum, right. Momentum is not conserved, clearly, because it's changing direction. All right, but angular momentum is. All right, so let's watch what the angular momentum is. It's just m r cross v. Okay, so that's the angular momentum. All right. The basic idea is that this area here, right, that is basically this perpendicular distance times this distance, right? So that's v delta t. And that's r perpendicular. Okay, so r perpendicular times v delta t. I multiply by m, and I get L delta t. So since L is conserved, it's going to be the same here as there. Basically that. All right, so the area swept out by the Kepler's third law will give you constant. All right, so I want you to show this in a little more detail in a way that is really quite different, okay, than the usual textbook. In fact, if you have an orbit going around an ellipse, the angular momentum is always conserved, and that's what you're going to show. So let's say r is a cosine omega t. Omega is some kind of angular frequency times I hat plus b sine omega t times j hat. Okay? If a equals b, this is a circle. Right? If a does not equal b, it's an ellipse. And the way you show that is if you take x squared over a squared and y squared over b squared, you get sine squared plus cosine squared equals 1. And that's the formula for an ellipse. X squared over a squared plus y squared over b squared is 1. That's the formula for an ellipse. Did you learn that in geometry? Yeah? Right? Remember that? I want you to calculate v by taking a derivative of this, and then I want you to compute L by taking r cross v. So you'll have two terms here. You'll have two terms for v. And then you cross product each of those terms. You'll have an I cross I, a j cross I cross j, etc. Go ahead, do it. First, calculate v by taking a derivative, and then calculate mr cross v. So work that out. Just take the derivative of r. Okay, that's your first step. And then take the cross product. So when you take the derivative, make sure in your v you have an I hat and a j hat. What's I hat cross I hat? 0. What's I hat cross j hat? K hat. All right, so you have to use that. Your answer will be proportional to k hat. But the answer you should get is a, b, omega, and then m. I think that's it. Is that right? Is that right? Is that what you got? Yep. So notice there's no time in here. No time appears. So that means L is a constant. So that tells you explicitly that if you have an elliptical orbit, no matter how it's produced, whether it's by gravity or something else, you will have conservation of angular momentum. Okay? Because elliptical orbits always come from forces that are in the direction of r. Okay, now we come to the third law, which is the most important from a computational point of view, and probably really is the one that made people convinced that Kepler was correct. To do this for elliptical orbits takes a lot of work, so I'm not going to do that. If you take a classical mechanics course later, you'll do it. But I'll just do it for a circular orbit. So we just used Newton's second law. So we have F equals ma. The F is gmm over r squared. M. What is A for a circular orbit? What is it? We did this many times. What's A for a circular orbit? V squared over r. So we have that. The masses cancel. And we get gm equals, what do we get? Gm equals r v squared. Okay? So we get that. All right? So usually we write v in terms of the period. All right? So it goes a distance equal to 2 pi r in a period t. Right? So that implies v equals distance over time, 2 pi r over t. So I stick that in here, and I get gm equals r times 2 pi r over t squared. Or I get r cubed over t squared equals gm over 4 pi squared. Okay, so this is Kepler's third law, that the radius cubed divided by the period squared is the same for all the planets. This is very accurately shown to be true. For elliptical orbits, you just put in r, gets replaced by the semi-major axis of the ellipse. And then it's still true. Okay? So you can use this to easily determine the period of any planet. If you know its distance from the sun, or if you know the period, you can figure out the distance. All right? That kind of thing is used a lot to look at like comets, things like that. All right? So this is Kepler's third law. So if I run this right now, I get a circle. All right? I chose values of x and v initially to get a circle. So you get a circle. Yeah, that's all right. Up here, what you see is a plot of the velocity in the y direction, the y component versus the x component. This is what's sometimes called velocity space. And you notice it goes from 0, from about a little over -6 to 6, so it's a little over 12, and the same in this way. So this curve is a circle. So here's the question. I'm going to change this from 6.28 to 8. So I'm not going to get a circle anymore. I'm going to get an ellipse. Now, you might have remembered what happened, but maybe not. And you didn't see what the velocity space did. All right. Now, before I'm going to initialize it. Before I run it, I'm going to ask you two questions. Question one is, I'm going to get an ellipse. Is the ellipse, now remember, now I'm giving this velocity a larger value in this direction. Everybody okay? So is the ellipse going to go like this, or is it going to go like this? Is it going to be a vertical ellipse or a horizontal ellipse? All right, so why horizontal? Because you remember that's what you saw before? Seems like you should get a vertical ellipse, right? You're giving it a higher velocity. All right, so that's question one. We'll see what the answer is. What about the velocity curve? What's going to happen to that? Are you going to get an ellipse there? So is Vx versus Vy going to be an ellipse? Well, you know, you took the derivative here. You get A omega cosine omega t, B omega sine omega t. Seems like you should get an ellipse, don't you think? Right? So the velocity curve, Vy versus Vx, should also be an ellipse. Does that make sense? How many people say yes? How many say no? All right. Let's see what happens. All right, so first of all, it went into a horizontal ellipse. And second, we have that curve there. Is that a circle or is that an ellipse? How can we tell whether this is a circle or an ellipse? Well, let's look at how this distance versus this. It goes from -5 to about 5. What's that, 10? And it goes from about -2 to 8. What's that? That's also 10. So the velocity space curve is also a circle. Hey, that's pretty odd. What happened? I thought I took the derivative here. So what that says is that A times omega must equal B times omega. All right? Is that right? Yeah. Somehow that must be right. How did that happen? So what's going on is it's the velocity, the velocity is not quite equal to this. Because notice this velocity space curve is not centered about 0. So in the y direction, it's centered about 3 rather than 0. You still get a circle, but the velocity space curve is shifted, even though the real space curve, the actual orbit, is an ellipse. Okay? So this is a good indication of how you have to think carefully about using intuition. All right? The important thing here is that forces don't change position directly. They change velocity. That's what they choose, right? Forces cause acceleration. And what we're doing by saying, by giving the velocity a bigger curve here, up here, we're kind of thinking, well, the force is the same. It's just going to deviate a little bit, and then it'll be an ellipse in the vertical. But that's not true. All right? You have to look at how it's really changing the velocity, and that we have a lot less intuition. Notice another thing here. Do you see how there are more dots here compared to here? Why is that? This goes back to something we did the first week of class. What does it mean when you have more dots here? Why are there more dots here than here? It's slower. The velocity is slower here, right? So in a given time, since it plots a point every interval of time, if it's going slower, it's going to plot more dots. And of course, that's true. You can see the speed here in the y direction is smaller than the speed there. The x speeds are the same. So that's why that curve looks the way it is. So it's a circular curve in velocity space. It has some interesting features. So if you really want to understand this, you should think about how to actually derive these results.